So today we're going to be talking about the trigonometry of right triangles, and we've talked about some functions, sine, cosine, and tangent. We've also talked about secant, cosecant, and cotangent, and we're going to utilize our trigonometry of right triangles foldable to help us solve a few problems. So we're given the very first problem, and it says to find the sine of theta, and we have a triangle here. We identify here theta, and it's a right triangle, of course. We have legs with a length of 3, square root of 55, and a hypotenuse of 8. So what we're going to do is follow our steps from our foldable, and let's take a look. First, I said locate the right angle, so here is the right angle. Then locate theta, and here's theta. And then we're going to label our triangle sides. So I know that this right here, this side right here, is opposite of theta. So I'm going to call this the opposite side. And I know that this side running right here is the adjacent side. So here is the adjacent. And then this, of course, is the hypotenuse. All right. Now, choose our function. So in this case, they mentioned that they wanted us to find the sine of theta. So sine of theta, Sohcahtoa. The sine of theta, as stated right here, is the opposite over the hypotenuse. So let me go ahead and write that down. Opposite over hypotenuse. And this is actually really simple because now that we've labeled opposite and hypotenuse here, it's simply 3 over 8. So our answer to this very first question is 3 over 8. So really simple. So let's go ahead and use what we've learned from the first example to complete the second one right here. All right. So this one right here says find the cosine of theta. So this one again is really quite easy. So here again is theta. This side right here is the opposite. And this side right here is the adjacent. And again, this is just to point out it's a right triangle once more. So therefore this is the hypotenuse. Okay. Now cosine of theta, Sohcahtoa. So let's go back, and here it is. The cosine is the adjacent over the hypotenuse. So here it is. So I'm going to go ahead and write that in here. Adjacent over hypotenuse. All right. So the adjacent in this case is the square root of 65, and the hypotenuse in this case being 9. Now I do want to point out, had we had a square root in the denominator, we would have to rationalize the denominator. We cannot leave the radicals in the denominator. But in this case, it works out just fine. So we're fine right now. Okay, so another quick example. But now let's take a look at this one. Now, in the problem statement that you might see on your assignment, you may not be given a picture. So let's not look at the triangle, all right? Let's just look at what we're given. All we're going to be given is this. Given sine of theta equals the square root of 3 over 2. So let's find the tangent of theta. All right, really simple to do here. Really simple to do. So let me think about sine and what it is. The sine is the opposite over the hypotenuse. Sohcahtoa, S-O-H. Well, if it's the opposite over the hypotenuse, then I can say that the square root of 3 corresponds to the opposite side, and 2 corresponds to the hypotenuse. So I've got a right triangle here, and I'm going to pick a spot. Let's say that theta is right here. So I drew a triangle already, a right triangle. Let's say theta's here. Opposite is this side right here. This is the opposite. This is the adjacent, and this is the hypotenuse right here. So I'm going to label opposite square root of 3 right here, this length right here, and the hypotenuse right here, label this 2. All right, well, now let's go back to what the question was asking. It said find the tangent of theta. Well, the tangent of theta is toa, the opposite over the adjacent, okay? And again, you can pull out your foldable activity, and here it is. The tangent is the opposite over the adjacent. All right, and let's see. What do we know? We know the opposite, we know the hypotenuse, we do not know the adjacent. Well, this makes this scenario really cool because now we get to apply one of the most famous theorems in mathematics, one of the most famous theorems in geometry, the Pythagorean Theorem. Alright, so let's write that down on our paper. So we know the Pythagorean Theorem to be a squared plus b squared equal to c squared. Okay, so there it is. A squared plus b squared equals c squared. But now let's label our triangle. We know this is A, side length A, this is side length B, and this is side length C. The problem is we do not know A, so we need to solve for A. So what we're going to do is manipulate the Pythagorean theorem just a little bit so we can solve for A. Well, it's really quite simple using a little bit of algebra. Not much algebra at all, actually. Cross that out. A squared equals c squared minus b squared. Well, we know what c and b are. Here's c, here's b. So I'm going to plug that in. A squared equals, and then c squared is going to be 2 squared minus b is the square root of 3 squared. Okay. Then we have a squared equal to 4 minus, and this becomes 3, so 4 minus 3, which is 1. So I have the case where a squared equals 1, and of course you apply the square root property to both sides, but very simple because the square root of 1 is simply 1. Okay, so the adjacent side is 1. Now to answer the question up here at the top, what is the tangent of theta? Well, it's the opposite over the adjacent. In this case, the tangent of theta will be the square root of 3 over 1, which simplifies, of course, to the square root of 3. So to answer our question, our very last question here, find the tangent of theta, the answer is it is the square root of 3. So hopefully these examples were understandable and you can complete the rest of your assignment on the trigonometry of right triangles.